Elevation.
Whatever the right
I'm terminated on the day of the AGM.
Oh, right, I see, okay.
There'll probably be some sort of ritual ceremony there going on.
They get exploded.
But there's time.
It's easy for a bit to figure out. Yeah.
Oh, speaker. This is a very much done. No, I wouldn't. No, yeah, no, I think
This is what happened when we considered the end. When it's
From the New York Times.
no, I'm just
Okay, I could speak loudly, but of course that probably won't be picked up by the online people, so I probably should wait till
I don't know, yeah. Well, really, you know, if other people want to, that's fine.
Shouldn't tap it. No, it's not good. Better do 1, 2 and hello London and things like that.
No, I would hate that too, even though you've got on stage and all this, but it's not the same. It's really, really not the same. I would cringe and die.
Hello? Oh, yep. Okay, good. Right. Welcome, everybody. Thank you for braving the cold weather today. We have a fair number of announcements, so we should get busy. Okay, let's go back to the beginning.
How can I get in there then?
Okay, firstly, as normal, this is a hybrid meeting. If you're online, I think there are quite a few today, then, and you're using Zoom, then just check you have the little green shield in the top left-hand corner. It means you're up to date and it's all nice and secure. You can ask questions at the end, but please don't put them in the chat, put them in the Q&A. That's right, isn't it, Pamela? Yes. Okay, so remember that. Okay, and then Pamela will read out your question for everybody here. Okay, NAM 2005. It will be in Durham on Monday the 7th of July to Friday the 11th. Registrations will commence at the end of January and stay open until the end of June. And please look out on the website, which I won't read out because everybody forget it, but it's available on the RAS website. And the announcements of the sessions will be made in February. Okay. It's some deadlines, RAS prizes and best PhD theses in astronomy and geophysics to be submitted. It says in 2023, but that's not very helpful. But remember to submit them. Getting quite a noise from somewhere. Yeah, and it's on. Oh well. Okay, these are the prizes for the best theses in astronomy and astrophysics, the Michael Penston Prize, and solar system science and geophysics, the Keith Runcorn Prize. And the instrumentation prize, which is the Patricia Tompkins Prize. The closing date for these nominations for all awards, which will carry a cash prize of £1,000 each and the opportunity to make a presentation at a future highlights meeting, is 31st of January. Okay, the grants deadline for the current grants round is 20th of February. And then it's my happy job to announce the 2005 RAS Awards winners. Do we have any in the room today? No, it's a shame. I was going to get them to stand up and take a round of applause, but they're not here. But if you're online, everybody sends their congratulations. So they are Honorary Fellowship, G. Catriona Jackman from the Dublin Institute of Advanced Studies, the James Dungy Lecture, Ryan Milligan from Belfast, the Harold Jeffreys Lecture, Andrew Valentine from the University of Durham, the George Darwin Lectureship, Dimitri Veras from Warwick. Group awards. The A is the European Pulsar Timing Array Executive Committee, and the G is MOSWOC, the Met Office Space Weather Research Centre. Early Career Awards. In G, Dr. Giulia Magnani from the Natural History Museum. Early Career Awards A, Niall Jeffrey of UCL, and Stephen Cunningham from the University of Manchester. Fowler Award G, John Coxon, Dr. John Coxon of Northumbria University, and A, Hannah Wakeford of the University of Bristol. Service Award G, Dmitry Storachak from the International Seismology Centre, and Service Award A, Professor Francis Keenan from Queen's, Belfast. Higher Education Award, Professor Andrew Norton of the Open University. Secondary Education Award, Alex Calvary of Surbiton High School. The Annie Maunder Medal, Ms. Amelia Jane Piper from Major Tim Space. The Jackson Gwilt Medal, Anna Moore from the ANU Institute for Space. The Price Medal, Paola Pinelli of UCL. The Chapman Medal, Nigel Meredith of British Antarctic Survey. The Eddington Medal, Professor Douglas Heggie from Edinburgh. The Herschel Medal, Professor Ian Smale from Durham University. And then the golds for geophysics, Professor Jonathan Tennyson of UCL, and in astronomy, Professor James Binney of the University of Oxford, as we know. Okay, so many congratulations to all our award winners. Of course, we'll be celebrating those awards at the presentation ceremony and dinner at NAM, which is not, the awards dinner is not in Durham, it's nearby, the coach ride away. Okay. Incidentally, the pictures of Bepi Colombo. It arrived at its orbit at Mercury. Not quite, it's got to descend to its full operational orbit, but the separation of the craft into two takes place this week. It was launched in 2018, so it's taken a long time to get there and several flybys. It has already generated a lot of scientific data and will carry on to do so. But this is taken from the BBC News website, so we thought it's worth repeating here. Okay, so now let's move on to today's program. The first speaker is online, I believe. It's Dr. Nilanjan Chowdhury, and the title is called Square Root of a Sonnet, which needs some explaining, I think. So, Professor Chowdhury is a Bangalore-based theatre maker and novelist. He has written 2 plays about science history, The Square Root of a Sonnet and The Trial of Abdus Salam, for which he received wide critical acclaim and has been staged across multiple cities in India, UK, and the USA. He's currently working on a new play about India's first woman particle physicist and has been part of over 300 stage performances with Bangalore's leading theatre companies, including the Centre for Film and Drama and others. Mr. Chowdhury's most recent novel is A Song of the Golden Sparrow, a fictional retelling of the story of free India. His previous novel, Shillong Times, is a coming-of-age story set against the ethnic conflict in the hill town of Shillong during the 1980s, and was nominated for the Indian Academy Prize in 2023. His earlier novels include the mythological thriller and contemporary detective caper set in Bangalore. Mr. Chowdhury is a postgraduate in physics from the Indian Institute of Technology, Kanpur. And I hope he's now online.
Yes, I am. Can you hear me?
We can indeed, thank you. I will warn you if you are close to 5 minutes from your time. Is that all right?
Yes, absolutely.
Okay. Thank
And
you.
I'm not. Thank you so much. I'm not sure if I'm visible, but I did see a glimpse of the hall and some of the people there and the speaker. So thank you all of you, especially Mark Lester, President Lockwood, and Steve Miller for inviting me for this session. Just a second, somebody's chatting on. Okay, yeah. Okay, so like you mentioned, I have 5 minutes, and one of the things I need to do in this 5 minutes is to explain what the square root of a sonnet is all about. Well, it's a play. It's a play about. Okay, thank you. You can see me. Right. Good.
Sorry, just to explain, you have 15, but I'll warn you with 5 to go.
Sure. I have 15, but of that, 7 will be consumed by a video recording of the play, which so therefore I'll cut my talking to about 5 minutes, and then you have 7 minutes for the recording of the play to be presented, which I hope has been set up on your systems. Is that okay?
That's lovely. Thank you.
Okay. So yeah, so like I was just saying, so the Spirit of a Sonnet is a play which, in fact, we performed last July, very close to the location where you're seated, which is at the Royal Institution, July 26th in 2024, and it's basically a play about two giants of modern astrophysics, Sir Arthur Stanley Eddington and Subramaniam Chandrasekhar. Eddington, of course, was the most renowned astronomer of his times, way back in the early and middle 1900s. And Subramaniam Chandrasekhar was awarded the Nobel Prize along with Willie Fowler from Cambridge for his work on white dwarf stars. I believe the reason that I've been asked to present here today is, is because it's a significant date, or will soon become a significant date. In about 3 hours' time from now, in India, the calendar will turn over to 11th January 2025. And it so happens to be the 90th anniversary of um, a fairly remarkable incident that happened at the Royal Astronomical Society halls 90 years ago, which is on the 11th of January 1935. So on that day, at another annual general meeting in winter, in January, Subramaniam Chandrasekhar presented his paper on white dwarfs. It was called The Maximum Mass of Ideal White Dwarfs, in front of a very distinguished audience, including people like, Hardy, Jeans, Fowler, Stratton, many others, and very importantly, Sir Arthur Stanley Eddington. Now, the paper that he presented, he had actually worked out at the age of 19, when he was traveling from Bombay to Dover to pursue his PhD at Cambridge under the guidance of Sir Arthur Eddington and Willie Fowler. And during that 3-month-long sea voyage, he essentially stumbled upon the fact that white dwarfs, which are at the end of their lives, some of them, not all of them, those white dwarfs which had a mass more than 1.44 times the mass of the sun, would start contracting and collapsing under their own gravitational forces and pressures, and they would continue to shrink until they became very, very small. I mean, and they turned into neutron stars, which would finally, in some cases, turn into black holes. Now, this was a remarkable piece of work for a 19-year-old boy. He did this in 1930. It involved, one of the things that it involved was, harmonizing the theories of quantum mechanics along with special relativity. And the people in the room, I'm sure, know much more about all this stuff than I do, but it had to do with what is called electron degeneracy, and, the particles inside a star gaining in mass and thereby intensifying their internal gravitational pulls, which would make the star shrink into a very small space, which later was discovered to turn into what we call black holes. Now, this idea of a massive object as massive as the sun becoming such a tiny thing was something that his guru and his mentor Eddington couldn't quite grasp and couldn't quite swallow. So there was a conflict between these two people, the very young and naive sort of Subramaniam Chandrasekhar and Arthur Eddington, and there was a sort of brutal public humiliation of Chandra on the meeting at the annual general meeting at 11th January 1935. A public humiliation which I think is sort of unparalleled in the in the history of modern day science, at least. And it not only took Chandra by complete surprise, because Eddington had actually been encouraging him all this while, but it also affected him deeply for several years. And he left the study of gravitational collapse of stars, and they weren't called black holes at that time, but he went to completely other fields, applied fields, hydrodynamics, stellar dynamics, radiative transfer, and various other things. And he returned in a way to the study of black holes only when he was about 63 in the 1970s. And the whole, however, during this long period, in spite of his opposition and conflict with Eddington, there was this strange relationship between the two of them, especially from Chandra's side, where there was a lot of respect. He sent Eddington food packets during the war when they had run out of food because of wartime rationing, and Eddington had stomach cancer. He paid glowing tributes to him, referred to Eddington about 11 times in his Nobel speech, and so on and so forth. So this is a sort of hero worship which continued throughout Chandra's life, although the hero turned out in certain ways to have feet of clay, by completely dissing a theory which later on came to be recognized as one of the first critical steps, the discovery of the Chandrasekhar limit, as one of the first critical steps towards the formation of a black hole, and indeed opened the pathway to the study of black holes themselves, which of course many people like Oppenheimer, John Wheeler, etc. contributed. But he was among the pioneers. Chandra was among the pioneers, and he had to wait 53 years, for his discovery to be finally acknowledged in the form of a Nobel Prize. So the play is really about the relationship between, apart from the science and works, but also the relationship between these two fairly complex characters, Eddington and Chandrasekhar. And the title of the play, The Square Root of a Sonnet, is actually paraphrased from one of Eddington's own statements, and I'm just reading it out sort of the way he said it. And he says, Eddington says, human personalities are not measurable by symbols, equations, or logic any more than you can extract the square root of a sonnet, which means that we don't often behave in very rational, ways, although we may be doing very rational work when we do science and mathematics. And this interface of the very rational world of mathematics and science, along with the very emotional and irrational world of the human mind, comes together in this play. The video clip that will follow is a scene from the play, very brief scene, 7 minutes from what is about a 2-hour long play. And it enacts a scene at the 1935 January meeting, when Chandrasekhar has just risen to present his paper on the maximum mass of ideal white dwarfs. I will let you take a look at the clip, and I hope it works. But the only thing I'd like to mention is many of the words, sentences used in the clip are quoted verbatim, in the sense that they're actually the sort of things that Eddington said. They're not the sort of thing that Chandra said, because it's an imaginary setting. He didn't directly retaliate in the meeting itself, but he did say some of those things post the meeting and the years that followed. But many of the things that you will hear Eddington speaking are actually words that I'm quoting verbatim from the actual incident. I hope I have not overshot my time on this little talk and the context setting. But if you're ready with the video, I think you should just play it. Thank you. Hello, are you with me?
Yes. We're just getting the video ready.
Okay.
I have a thumbs up from the projectionist, so.
Okay.
The publisher will now present its paper. President Stanton, gentlemen, my paper on maximum mass of ideal white dwarfs. In conclusion, for a star of small mass, the initial white dwarf stage is a natural step towards complete extinction. But for a star of large mass, one is left speculating on other possibilities. Thank you, Chandrasekhar. Thank you, sir, on that very enlightening talk. Thank you, sir. Are you quite done? Yes, sir. Good. Yes, sir. With permission from President Stratton and the August audience here, I'd like to say a few words of my own. But I don't know whether I'm going to make it out of this meeting alive. The paper that you just heard, foundations are completely wrong. No buts. There's a no buts. I have discussed this with you earlier, and you refused to see reason. President Stratton, members of the Royal Astronomical Society, it's my painful duty to inform you Mr. Chandrasekhar has put the stars in precisely the same difficulty in which Professor Fowler had rescued them earlier. Chandrasekhar has put us in a very difficult situation in which only an accident may intervene to save these helpless stars. And I, for one, need more protection than that. You've seen my paper, you've reviewed all my calculations, you've just... Mr. Chandrasekhar, you have had for 30 minutes, no less. Kindly allow me to have mine. Yes, I've seen your accounts. And I have come to the conclusion that they are reductive and absurd. My equations are absurd, but you said... I said your equations are a combination of relativistic mechanics and non-relativistic constant theory. And I do not regard the offspring of such a union to be born of lawful wedlock. Yes, he did. But his conclusions have nothing to do with yours. Gentlemen, I believe there should be a law of nature that prevents such stars from behaving in such an absurd manner. Nothing short of stellar movement. Thank you. I have nothing further to say. They all laughed at his outlandish theory. Not one person in the room stood up. Not one person. The meeting was called to an end, and the room emptied out. They're like a fool. Kept hitting glances at me. Looked at, came around, patted me on my shoulder. Too bad. Too bad, boy chap. What then they would say. That evening, turned to him. Bare to face the empty rat hole of a house in which I was living. I went down, common room in Trinity College. I am it's near the envelopes. The lines from Eliot's Hollow Men running inside my head. This is the way the world ends. This is the way the world ends. the bank. That winter's evening in January, my world it ended.
Okay, ladies and gentlemen, I hope that clip was audible and visible.
The laughter is because it was a bit more than audible to start with. We had the sound up far too high. And so the applause was almost deafening to start with. But we sorted it out and we heard the rest perfectly. So thank you very much. So that's why people laughed, not the content. It was because it was very loud. It was our fault. So I'd just
Okay.
like to stress for the next speakers, that's not going to happen again, all right? So could you take some questions from?
If like there used to be a advertisement for watches in India. If you have the time, I have the inclination.
Do we have any questions in the room? Yes, Stephen. Oh, here we go.
Yep. Oh, no, you hang on. Just, thank you.
So, Nilanjan, are there plans for bringing the play back to the UK? I think you're in discussion with the Murty Foundation at the moment about doing something in Cambridge that maybe the RAS can be involved with as well.
So first of all, Steve, if you're present in the room, I'm glad to see you're up and about. And on the second part, yes, we would love to come back if you'd like us to be back. And yes, we are in talks with the Murthy Foundation. And they have evinced interest in actually maybe doing something in cooperation with the Royal Astronomical Society. So yes, like I said, if you would like to have us, we would like to be there, and we will try and see how we can make this financially and practically feasible.
I think we have a question from Ian Robson online, Pamela. Okay, he's raised a hand. I'm not sure we can deal with that, can we? Ian, yes, well, I'd agree with him there. Ian, if you could put it in the Q&A, then Pamela can read out your point. I would just make the point that what made Eddington's behaviour even the more remarkable was the man was a Quaker and had been quite known for his kindness, and I just don't understand where it came from. I really don't. And I do know that a lot of people wrote to Chandrasekhar afterwards saying, he's got this wrong, he's got this wrong. So it took time, but the reality and the truth outed in the end. But it was a remarkable outburst. Do we have any other? Yes. Just hang on a minute because people won't hear you online. So.
Thank you very much indeed for that wonderful play. And if it does go up to Cambridge, I'll certainly come and see it. I just wanted to ask you, there's a huge interest in the lives of scientists. And as you know, for example, Sinishrava Ramanujan and the wonderful play about the man who knew infinity turned into a film. And I just wondered if you had any plans to address any other scientists in your artistic work.
Yeah, so this is for me, I assume. Well, yes, so as we speak, we've started rehearsals on my second science play. It's called The Trial of Abdus Salam. Abdus Salam, as you know, was the Pakistani physicist. He was the first Pakistani and the first Muslim, in fact, to win a Nobel Prize in science, the second ever. Well, that plays around, in a sense, his complex relationship with his country, which is Pakistan, and that also has a very strong, British connect, because he did a lot of his work in Imperial College. His wife Louise used to be in Oxford, and so that's the play we are rehearsing, and we hope to put it up in Bangalore starting March 29th. And as the gentleman mentioned at the beginning, I've also just finished the first draft of a third play. I wanted to do a trilogy of science history plays. I've done a third play, written a third play called Invisible Particles, tentatively named, which is around India's first woman physicist, not just particle physicist, but woman physicist, a lady called Bibha Chaudhary, who has been completely lost to history, completely forgotten. And her life intertwines very closely and strangely with another woman physicist, Marietta Blau, whose work on nuclear emulsions finally led to the discovery of the meson, which is later called the pion, for which Cecil Powell and people from Bristol University were finally acknowledged as having discovered the meson. So yeah, that's what's on my plate right now. I hope I've answered your question.
Yes, you have. Thank you very much.
Thank you.
Thank you very much, Nurjan. I just have one question for you, a brief one. Do you
Yes.
think the reference to the square root of a sonnet was by way of some sort of apology? Do you think he was apologizing for his own actions by saying that?
No, not at all, actually. So he was, as you know, a very gifted writer and gifted orator. He was very, very fluent with his language and words. I think typical of the Cambridge Dons at that time, multifaceted. So this particular statement had nothing to do with Chandrasekhar. It was just emerged in one of his speeches or writings, and in fact, he never apologized. So there is one quote, if I may, because it's so biting and it's so witty at the same time. I think in 1939, Chandra wrote a book, he wrote a book which basically summarized all his work around collapsing stars. And Eddington took a look at that book and he said, "How nice to get everything wrong in one place."
Oh dear. Sometime one could be cursed by having a good wit. So.
But the whole play is this whole very bizarre episode, and why a man as distinguished and as in a way broad-minded. There was no racism and colonialism, to the best of my understanding, which was at the heart of this matter. Why he did this, and if you read the play, by the way, if somebody wants to read the play, I'd be happy to share a script with them. Please contact me through someone at the RAS by email. But the play really explores these potential, reasons why this thing happened. There is Eddington's own very strong views on how nature should work and how God should have constructed the world. He was very devout, and there are other things. So the play is an exploration of those possibilities.
Okay. Well, thank you very much indeed, Nurjan, for the play and for the clip we've seen today. So thank you very much.
Thank you so much. It's been a pleasure and an honor. I never dreamt that I would be speaking to people at the Royal Astronomical Society in my life, but stranger things have come to pass. Thank you.
Maybe in person one day soon, that would be good.
Hopefully, yes. Thank you.
Right, we should move on to Harold Jeffrey's lecture. It's Dr. Jessica Irvine from Bristol University. Jessica received her MSci in 2005 and her PhD in 2009 from Cambridge University, where she also worked as a postdoctoral fellow. She was an assistant professor at Princeton and now an associate professor in global seismology at the University of Bristol. Her research encompasses Earth's core, mantle and oceans, as well as Mars and other planetary bodies. And her Harold Jeffreys lecture is entitled Hearing Planetary Hearts, Seismology of the Cores of Earth and Mars. Jessica. I think
Might someone tell me how to change slides?
I think if you say next, he'll do it for you.
Looks like you're gesticulating as a remote control, this one. Okay.
There we go.
Fantastic. Okay, with that set and with the promise that the RAS treats its speakers slightly more kindly today than they did in the past, I am absolutely delighted to be here to talk to you today about how we seismologists hear planetary hearts. You'll see several names on the screen right now and many other names scattered throughout this talk, but I'd like to highlight Ved Lekic and Sana Kotar, two of my long-term collaborators, PhD students who've graduated despite my supervision, Wembo Wu, Stuart Russell and Kat Dupre, Frederick Simons and Joel Simon, who I work alongside on Mermaid Project, and the entirety of the Insight Science team, the research from which will form the latter part of this talk. I'm very aware that this is the Harold Jeffreys lecture, and so you'll also see scattered throughout this talk various vignettes of things that Jeffreys was thinking about, because it turns out that Harold Jeffreys was also deeply fascinated by how we could seismologically understand the cores of planets. So how long have we been hearing about planets? Well, one-dimensional, radially dependent estimates of what is going on inside Earth's core have evolved substantially over the past roughly 130 years. However, on Mars, we've been trying to think about what the red planet means to us and what it is at its heart for probably millennia, but we only have 4 years worth of seismic data from 2018 to 2022. So throughout this lecture, I'd like to talk to you about what we've learned of the cores of Earth and Mars, and I'll wrap up by telling you what my biased opinion is on where I think we could go from here. You'll see at the side of the screen a small timeline. So we're going to stretch all the way back to some of the first ideas about Earth's core, and through the talk we'll move down towards the bottom until current and future research. So let's begin back at the beginning. I don't expect anybody in the room to be rapidly translating German in their heads, but if you were, you would be reading research from 1897, where Weichart was really thinking about what could be at the center of the Earth. He wasn't using seismology, but he estimated that there was some distinct kernel or core deep within our planet. His estimate of size was a little different to what we think about today. He was thinking about something which occupied 4/5 Earth's radius, leaving only the top 20% of Earth to be comprised its rocky mantle and crust. So this is our nearly 130 years ago record. And still more than 100 years ago, we could move on to the work of Richard Oldham. His text is fortunately for our purposes in English. And he tells us that the central, approximately 4/10 of the radius of the Earth, are occupied by matter possessing radically different physical properties. We think that his seismology may actually have been a little bit sketchy, but this is a seismological estimate of what is happening in the middle of our planet. And by that estimate, the middle of our planet is distinct, our planet is differentiated, and Earth has a central core. And we've spent all of the last years since then trying to work out what on earth is going on. So as we step forward slightly in time to 99 years ago now, so we're moving swiftly towards the events we've just heard about in the last talk, it turns out that Harold Jeffreys was having these self-same thoughts. He was actually trying to understand the rigidity, the physical properties of Earth's core. This is in a paper published in 1926 in an RAS journal. And he brings together the non-seismological ideas from 1897, together with the ideas of Oldham in 1906 and Gutenberg, who arguably did a much better seismological job, and tells us that indeed the observations these scientists made are of the same central object. There is a rocky mantle and then a metallic core. And importantly, from what we understand of Earth's core now, he says that there seems no reason to deny that Earth's metallic core is truly fluid. So we've moved from having no core at all to thinking there might be something down there, to seeing it with seismology, and now stating clearly that Earth's core is metallic and that that core is fluid. And these are both pieces of information which are very strongly based on the seismological evidence. We can step forward again in time. And in 1936, so now we're after the events we've just heard about, Inga Lehmann published her groundbreaking, illuminating research into core transiting seismic waves. She had discovered Earth's inner core. Inside this fluid outer core, there is a solid metallic body. And so we see on the screen here estimates that Jeffreys had made by 1939. He built a seismic model of the P-wave velocities of the entire Earth, including Lehmann's inner core. So we see this central inner core inside the fluid, low velocity outer core, and then we see the rocky mantle in roughly the top half of the planet. Some details of this model have proven to be very robust. Others, I will say, have since been revised. That dink in the curve vanishes if you wait long enough. So we have models of Earth's core from the 1930s. What techniques do we have available to us to see into a planet? Body waves are the method that Jeffreys' early research was using, that Oldham's work was using, that Gutenberg's work was using, that Lehmann's work was using. Body waves are elastic waves which propagate from an earthquake, and they are detected at a seismic sensor. We call that a seismic station. And you can see an example of a recording of a body wave from a seismometer in a basement of a building I was working in on the screen. We have two sorts of elastic waves we tend to look at. Compressional waves are called P waves. They travel more quickly than shear waves. Shear waves can't propagate through fluids. So if we want to look into Earth's core, we're looking for compressional waves. And those compressional waves are sensitive to the velocity along what's effectively a ray path, although in reality, the physics of the case is that there's a finite volume of sensitivity. In addition to those body waves, there's another technique which has proven equally valuable for looking into the heart of a planet. And those are Earth's normal modes of oscillation. So these are free oscillations of the whole body, so the entire planet is vibrating. They're excited by the largest of earthquakes we experience. These normal modes have different patterns of vibration and different sensitivities to velocity and density at different depths in the Earth. The modes can have very long periods. So the modes for which you see cartoons on the screen have periods of the order of tens of minutes for a single oscillation. These are excited by those large earthquakes, and then they rattle away. They're recorded for days afterwards. Variations in the radial or 1D structure of the Earth change the center frequency of these oscillations. But if we have lateral or 3D structure within the Earth, they break the mode degeneracy, and we hear a splitting of the peaks, slightly discordant, very similar pitches of Earth's vibration. These mode data were investigated primarily after the Second World War. And so if we step forward again, still in Jeffreys' history, to 1967, we find that Jeffreys, in a very brief paper with a rather straightforward title, The Radius of the Earth's Core, was indeed trying to estimate the radius of Earth's core. And specifically, he was now trying to compare these normal mode frequencies with body wave travel times to try and harmonize the results and seek consistent ideas about how big this central metallic body buried within the Earth might really be. These normal modes were really key for another aspect of understanding Earth's core. In fact, they were key for understanding the nature of the inner core. Although it was proposed that Lehmann's inner core was solid, this proved remarkably difficult to actually pin down and verify. It had long been suspected, but it was these observations of these whole Earth oscillations which could not be satisfied by a fluid inner core, and proved definitively that the inner core must be a solid. And so we get to models like the one published here by Adam Jaworski in 1971. This is the velocity on the lower line and the density on the upper line of Earth's core. So the velocity of seismic waves and the density of that iron alloy material. The updates that were made using these normal mode data helped verify that the core was solid and gave us models where there was a distinct difference between the fluid outer core and the solid inner core. So if we look at what happens at that boundary between the outer core and the inner core, we see substantial jumps in the density and velocity at that interface. And we see that the shear wave velocity, which must be 0 in the fluid, jumps up to around 3.5 kilometers per second when we enter the solid inner core. So we've moved ourselves forward in time. We've talked about the big discoveries in 1D properties of the core. What's happened since then? What do I believe are the big highlights? It's my lecture. I get to tell you my opinion on such things. And we've seen other big discoveries about these 1D big average properties of the inner core. In a pair of papers published back to back in 1986, it was proposed that the inner core was anisotropic. That's a material property that tells us that the elastic properties of core material inside the inner core are different if you go in the north-south direction compared to if you go in the east-west direction. So that was 1986, that's still not super recent. Subsequent work has proven that that's not a uniform property, but that varies in 3D across the inner core. After that, there have been multiple attempts to try and detect seismic shear waves which travel through the inner core. They have to convert to P waves when they're in the fluid outer core, and these detections have been proposed by a number of illustrious scientists, including those who've spoken in this very room. These detections, however, remain very rare, and it's possible that these inner core shear waves, called in one undergraduate textbook the holy grail of global seismology, might in fact just be lucky observations. It might be very difficult to see shear waves in the inner core routinely. And finally, an innermost inner core, so something about the center of the inner core, may be different to the rest of the inner core. This could just be distinguished by a change in anisotropic texture, but there may be something different about the very center of the inner core. These are all these big one-dimensional properties of the core. We've been mapping them for nearly 130 years with geophysical methods, especially including seismology. So should we keep on trying? Is there any point in trying to understand the 1D properties of the Earth's better? Are the discoveries still to be made? I think straightforwardly, I believe the answer there is yes, even if we're just thinking about this 1D radially varying structure. And so I'm going to spend the next few minutes telling you about a model that I have built with my collaborators. We believe it's a better model of the properties of the outer core. Why might we want a new model of the outer core? Well, here I can show you a compilation of velocity models for Earth's outer core. On the far side of the screen, we see the core mantle boundary with lower velocities. And on the nearest side to me, we see the inner core boundary. And although you might believe that these different colored lines look like they overlap quite well, this is the largest fluid body on our planet. And we don't agree on what the seismic velocity should be. We can tell these lines apart. We don't know what the velocity is, especially at the top of the outer core, we can see the full rainbow of lines. And the long-standing Earth model, PREM, the preliminary reference Earth model, seems to disagree with body wave data. So we've got some seismic observations which don't match velocity models of the outer core. So it seems like maybe we should try and do something about that as seismologists. This is one example of the ongoing questions that remain about the core's elastic properties and how we might understand them and what implications those have for Earth's evolution. So how do you build a better model of the outer core? We seek a model that tells us about velocity and density as a function of depth as we go through the core. And we expect that the outer core should mostly be a well-mixed liquid. So to build a better core, we enforce that assumption. We therefore choose to seek the equation of state of the outer core. And some people who are listening might think, equation of state, that sounds like a vaguely familiar thing that was once spoon-fed to me in a lecture. To remind you, an equation of state relates the physical properties of material. And the sort of equation of state we choose to use can relate the pressure, the volume, and the bulk modulus and its derivatives of a material, so we can move between those real physical quantities. So in seeking velocity and density via an equation of state, we end up allowing ourselves to look for a mineral physics-based parameterization. We can also use new data. The sort of data that we choose to use are those normal mode oscillations. And here I show you a somewhat alarming animation. Don't worry, this is exaggerated both in amplitude and in time. This is, though, the example of the pattern, if not magnitude, of surface displacement we'd get with one of these normal modes. We used a whole array of normal modes. These aren't our own measurements. They're taken from a wide range of academic sources. These are not easy measurements to make. And we have assembled a set of 319 of these observations. About a third of the observations which are sensitive to the outer core are new since our standard PREM model was built. So we have some new data in. And we built a model. I'm going to show you our model. We call it Epoch Vinay because it's the elastic parameters of the outer core, and it's a Vinay equation of state. It doesn't quite roll off the tongue, but it's not terrible. I'm going to show you Epoch Vinay in green. There are, in fact, error bars, 95% error bars surrounding that green line. They're just so tight in, it's virtually impossible to see them. And we see the older model, PREM, in orange. These two models seem to diverge a bit near the core mantle boundary. And if I enhance that bit of the image here, we see that our normal mode data have a lower seismic velocity than the long-standing model. This was really good news from our perspective. If the body wave data, which we didn't use in this sort of work, wanted a lower velocity, our new inversion for the 1D properties of the outer core also tell us they need a lower velocity. We're starting to reconcile what seem to be troubling differences between different kinds of seismic observations. We have velocity as a function of depth here with those very small error bars that you can nearly see on the enhanced figure. Our resolution of density in the outer core is much less good. So here I show you the density that the normal modes seem to call for in the outer core together with PREM. And you can see that that density is actually higher than the long-standing model. That creates a little bit of consternation when we looked at those results, but the normal modes do strongly prefer this. And that tells us that we need to think about where we might have mismeasured the mass of the rest of the Earth. That's likely to be compensated for somewhere in the silicate crust and silicate mantle. So this is the model. This is what the seismologists wanted. But what does that mean for those of you who are not seismologists? We have mineral physics results. There are things we can talk to our mineral physics colleagues about. We know that the bulk modulus of our model is a little bit smaller than that used to be believed. But the pressure derivative of the bulk modulus is a bit higher. The material of the outer core is a bit squishier, a bit more compressible. When we look at the density at zero pressure, although in the outer core the density is higher, the zero pressure density is a bit lower, which leads us to believe that there might be slightly more light elements, non-iron elements, in the outer core than had been thought before. There are some caveats. So we can't independently constrain a mass and a volume. They trade off perfectly because we're really sensing density. And so we had to pick a mass, and we did that. But we've developed a new model that tells us about the physical properties of the outer core using only 3 parameters and the one we've chosen. So we've reduced the number of free parameters, and we've developed a model which does a better job about telling us about the physical properties of the largest fluid region of our planet. We used a Bayesian approach for this work, and we had to assume that PREM worked well in the rest of the Earth. We believe our model is better. Of course we do, it's our model. We also know that it does have a mineral physics base under it. We fit the normal mode data, these low frequency oscillations, better than existing models. We also do a better job at predicting a completely independent seismic data type, body waves, than PREM can do. I've told you that this model has a denser outer core, and we need to think hard about how to compensate for that. It might well be that there are other changes that would help the data be better described. For example, the PhD work by Stuart Russell, which I highlight here, suggests that we may also need to change our models just above the core mantle boundary in order to better depict these deepest parts of the Earth. So did we settle this question about whether there is something different at the top of the outer core? We've built a nice smooth model which doesn't require any differences, but we don't rule them out. What could differences at the top of the outer core, as revealed by a seismic model, mean for our understanding of the core? It could mean one of many things. We would call such a layer at the top of the core, a stratified layer at the top of the core, an E-prime layer. We'd follow some very seismologically geeky terminology developed by Bullen and used for many decades. So if there was a layer, what is it? Why is it there? It could be a layer of light element scum. Released as the iron-rich inner core grows, light elements are expelled, they go preferentially into the fluid, they could float to the top. Such a stratified layer could instead be caused by immiscible melts at the conditions of the core. So it might be that different iron alloys don't mix, and that's what we're seeing. Some people have suggested it could be a relic of planetary formation, so it's primordial. Other people have even argued that it could be related to the giant moon forming impact, leaving a layer of scum at the top of the Earth. That's not a value judgment on this layer, by the way. That's rather to say that it would float and be distinct. It's possible that transient amounts of silica or magnesium iron silicates could collect at the top of the outer core before their light nature, their high buoyancy, leads them to be incorporated into mantle flow. So we could instead be seeing a rather transient material which is constantly replenished. Or such a layer could be part of the story of the mantle being very slowly dissolved into the core. It could be FeO going from the mantle into the core, or it could be hydrogen from subduction that gets to the core mantle boundary and then gets sucked into the core. We don't know, and some of these processes may well be happening together. So we've built a better model for Earth's core, but there are still questions about the 1D properties of the planet we have been studying seismologically for more than a century. There are questions ongoing, and we've not finished our work on Earth's core, but I do want to shimmy forward towards other cores. And therefore, I jump at this point from Earth, fortunately back to Jeffries, because it wasn't just Earth's core that Harold Jeffries was fascinated by. It was also Mars's core. And so now I can show you a figure from one of Jeffries' works about planets, not just the Earth. This is a paper from 1937, again, another distinguished publication, RAS journal, where Jeffries was trying to hypothesize about what density could look like in the telluric planets. So we had a decent idea of the density distribution at this point inside the Earth. The results for Venus, I think, are highly speculative at this point. And in fact, Jeffries has to make 2 possible models of what's going on inside Mars because it was very unclear what was actually happening there. Jeffries wasn't the only person who's tried to build models of Mars's structure, but he was certainly one of the earliest as he made these density estimates. And so now our timeline has changed to red. I'm going to spend this portion of the talk exploring the red planet, the history of discoveries, and what we can understand about its core. So, how do you estimate what's going on inside the core of an entirely separate planet that no human has ever set foot on? We do have some information already about Mars before the seismologists got to throw their instruments onto its surface. We have geophysical constraints. So we understand the mass, the moment of inertia, and the rotational properties of Mars. It has 2 very small moons, which help us out with those. We also have geochemical constraints. So we know firstly that Mars itself as a planet should be made from a reasonable mix of material which was knocking around the early solar system. We also have Martian meteorites, and you can see a very large picture of a rather small meteorite on the screen right now. We have meteorites which have come from Mars. And so we know that the material that formed Mars, that composition should evolve over the course of roughly 4.5 billion years, and it should lead to the formation of rocks like the Martian meteorites we see today. So what did we know about Mars already? A good amount without any boots on the surface or seismometers on the surface of the planet. So what were these early ideas about Mars's properties? We're going to talk about a couple of studies from the late 1960s and early 1970s. And it's worth saying at this point, there were still arguments about whether the core of Mars should be iron-rich like the Earth, or whether the planet could have differentiated at all. But one of the big questions that was out there was what was happening with the thermal state of Mars's core. Because Mars is quite small, its radius is about half that of Earth, and small bodies cool more efficiently. So should Mars's core be solid? Here are some of those early models. And we see in the models the grey and red lines from Binder's seminal work in 1969, where the core is thought to be solid. The planet is small, the core is cold, it's solidified. By the time we get into the middle of the 1970s, those ideas look different, and the models shown here in blue have a lower density because the core is liquid. So we now believe, and we now in fact know, that the core is liquid. That's from a few different pieces of non-seismological information. So we can look at the love number of Mars and say that it rotates like something which isn't solid all the way down. We can also talk about the anticipated composition of Mars. The sulfur we expect to be present in Mars's core virtually acts as antifreeze, and it could help the temperature leave the core still a liquid. So we can go from those earliest models to what I would technically term a whole zoo of models that people have developed since. There are more coloured lines on this figure than there are sensible colour choices to be made. People have spent a long time thinking about internal models which could tell us about the size and physical properties of Mars's core. These models are testable. So did we try and test them? Yes, many people have tried to test models of Mars. And in fact, the Viking missions sent seismometers to Mars, landing in 1976. Unfortunately, from what I understand are basically political considerations, the seismometers were on the top of the lander and not on Mars. And as a result, they didn't detect any verifiable Mars quakes. So in the 1970s, those models couldn't be tested. However, we've moved on since then. And the InSight mission was a landed geophysical mission. It's a solar-powered mission with several different geophysics instruments, but as seismologist, I believe that by far the best instrument that it took all the way to Mars was SEIS. SEIS has a very broad band and a short period seismometer, and they sit nicely under a hat, which acts as a wind and thermal shield. So could sending a seismometer to Mars tell us anything about its core? Could we see its core? We certainly hoped so, because that was one of the primary mission goals of the InSight mission, to measure the size and state of Mars's core. So the idea goes like this. You wait for a reasonable sized Mars quake, and there are various definitions of reasonable, and you seek waves which are reflected from the core. A liquid core can't transmit shear waves, so we're going to seek shear waves which have been reflected from the core. We're going to seek a particular polarization, transversely, horizontally polarized shear waves. To seek those, we need to know where our Mars quakes are. And so all of the Mars work that follows relies heavily on the work of the Mars Quake Service, which detected and located quakes on Mars. So we seek the energy which goes from a quake down to the surface of the core and then gets reflected and comes back up. And you already know that I wouldn't be telling you about this if it didn't work. So let's see what worked. You're seeing a seismic record from one Mars quake. The easily detectable signals are those which travel straight from the source to the receiver and give us the nice strong arrivals between -400 and -300 seconds on this seismogram. I could maybe convince a couple of people in the room that there's something really interesting on this record at the 0 mark. In fact, we believe that there's something really interesting at the 0 mark is the seismic arrival of a wave reflected from the surface of the core of Mars. However, reasonable people probably wouldn't be convinced. And so we added up or stacked many different seismic events from Mars. With those seismic events, we got records like the one at the bottom, where there is a very clear signal, at least in seismological terms, of energy which is reflected from the core of Mars. If we can see seismic waves bouncing from it and time them, we can tell you how big the core is. The core was bigger than many of the pre-existing models, although it fell just within the bounds. And that large core must have a relatively low density in order to get the mass of the planet right. So seismically, we can now tell you that there are a significant degree of light elements in the core of Mars. We weren't content there, though. InSight was originally set to last for 1 Martian year or 2 Earth years, but it was extended by NASA. And that turned out to be very good indeed for seismologists, because in the second half of the InSight mission, 2 very large seismic events were detected on the far side of the planet to where the lander was. One was relatively well located at the end of the Valles Marineris. The other was a bit trickier to locate. We didn't pinpoint a location immediately, but we were able to draw an annulus of where we thought that second seismic event might have happened. Because they're on the far side of the planet, we hoped that we could detect energy going through Mars. But that second event was quite hard to work with because we couldn't tell precisely where it was. It was classified as a quality B event. It wasn't top-notch. However, our colleagues on Mars satellite observation missions really came to our rescue. Because although that event was quality B from seismic purposes, it turned out you could see it from space. Specifically, this wasn't a Mars quake. This was a meteorite impact on the far side of the planet, which generated big enough seismic waves to travel all the way across Mars and could be imaged in a pair of day-separated satellite images. So this giant impact we knew was responsible for the seismic signals that we were seeing. And that meant that we could completely constrain how far away the second event was and precisely where it was. We could try and use these 2 extra events to tell us something about the core of Mars. So we looked very hard, and very many people did this, at the seismic records. And although I can highlight something in pink and throw it on the screen, the seismograms by themselves weren't very convincing. We did a lot of seismic processing, and we discovered that if you look at the amount of vertically polarized motion compared to the amount of horizontal rectilinear polarized motion that our 3-component seismometers detected, there were in fact some clear peaks that you couldn't see in the raw seismograms themselves. We'd managed to observe seismic waves traveling through the core of another planet. So what did we do? We wanted to know what Mars's core was like, so we built seismic models. We inverted the seismic signals from these 2 quakes, together with a whole bunch of other seismic observations from Mars, to build the first seismically constrained models of Mars's core. We also had to go at re-estimating the density and radius of Mars's core. We used a couple of different inversion schemes. We used those different inversion schemes, slightly different data sets, to give us a sense of the uncertainties introduced by our modeling choices. Science is done by humans, we make choices. By making 2 different sets of choices, we could at least see what we were messing up. And we also inverted our data without those vital core signals to see if they truly were vital. So without further ado, we now have models of the density and velocity inside the core of another planet. One set of inversions are shown in blue, the other set in orange. And while the details are rather technical, we can see quite clearly that those model families overlap. The different approaches agree. We're not dominated by choices that we as humans have made. We see whatever model you choose, the average velocity at the top of the outer core is about 4.9 kilometers per second, given particular assumptions about the mantle. If you change your mantle mineral assumptions, you still have a velocity that's 4.9 or 5.0 kilometers per second. This is within the range of pre-landing estimates, but falling slightly to one side of the bulk of them. We're learning something new about the elastic properties of another planet. In the panel far to the right of the screen, we see in grey what would happen if you tried to work out the elastic properties of a planet without waves which go through the core. Even with two data, those two quakes, we're seeing a substantial information gain. So we're doing a much better job when we introduce information about seismic waves which go through the core. And that shouldn't be a surprise, but it was certainly a relief. The models that we developed have a core mantle boundary radius which overlaps with the earlier discovery I told you about a few slides ago. It also overlaps with several subsequent studies that looked for those reflected waves. There are trade-offs inherent in this work. So you can fit the data by making the core slightly smaller and the density slightly higher. But those trade-offs are within the uncertainties that I can tell you about today. They're not overwhelming. Our new data have provided important sensitivity to the core's elastic properties. I mean, primarily, we've got the best ever estimates of velocity in the core because they're the first detections of something going through the core. The form of these curves is again constrained by mineral physics equations of state, as we did for Earth's core. So we've brought some mineral physics in there. I would caveat that the new data we gathered are not helping us understand more about density. These body waves don't do a great job at that. But we've discovered the elastic properties of the core of another planet. And we haven't had to make any assumptions about what that core is comprised of. We've made some assumptions about the mantle, but we haven't dictated what the core should be made of. So obviously then the next question was, what is it made of? We've got the elastic properties and the density, so we can try and narrow down core composition. We have models that we've created, shown in orange in the figure here, and models that weren't informed by our new data shown in grey. And we'd like to try and find some composition which fits the models we've created well. We'd like to go for the bullseye in the middle of the orange blob, if you will. If we just took a core which is made of iron and sulfur, you'd need so much more sulfur than any cosmochemist will ever agree to. It's not reasonable, it's not feasible. We could try and ameliorate this situation. We could add some oxygen. That doesn't actually help you out. You should add some oxygen anyway if you're building a core for Mars, because if sulfur goes into the core, oxygen will go with it. But it doesn't fix our problems. However, it turns out that if you add oxygen and sulfur and carbon and a sprinkling of hydrogen, you can represent the properties that we see for Mars's core well. So you can do a good job providing you put in the right mix of elements. Of course, we're seismologists, we like making models, we inverted those again. You have to be really careful, we're inverting the results of an inversion and we have to make assumptions about what's going on in the mantle. But roughly speaking, we believe that 20% or a fifth of Mars's core is likely to be light elements, dominated by sulfur, but with maybe 0.5% hydrogen present, as well as oxygen and carbon. So we're able for the first time to give you seismically informed estimates of what the heart of another planet is made of. This was work, again, done by a very large team. And if I had time, I'd read out all of their names because there was a huge amount of effort that went in here. Instead, I'll briefly put the names on the slide. And if you want to know more about many of these people, you can come and talk to me afterwards. So we built a simple model of the interior of Mars. It has a silicate crust and mantle and a liquid iron core. And we can look back to Jeffries again and say, what should we be thinking about? When he was trying to build his own models of Earth's core, Jeffries had some caveats you should think about when making model choices. His models, he said, were always subject to the condition that no unforeseen complications may be present, but the onus of proof is on the advocate of such complications, and they must be stated in a form leading to verifiable inferences before they can be discussed. He also then went on a footnote about Alice in Wonderland and the Cheshire Cat. We won't dig into that too deeply, but I'm sure you can find this in the records of the RAS journals, should you so choose. So should we be thinking about a more complex interior? Maybe. We have the hint that something more complicated may be going on. Specifically, when we look at the seismic signals from that giant impact on the far side of the planet, there is another faint, vertically polarized signal present. The big mantle arrivals are lined up at 0, and I've drawn a couple of red circles where there's just a hint of some seismic energy coming in. It's vertically polarized. It doesn't really fit well with a simple 1D model of Mars, as I've described already. But if Mars's mantle was layered, we can ask, could there be a seismic wave which interacted with a distinct layer at its base, a molten basal layer? Yes, there could be. If there is a molten mantle layer at the base of Mars, you could generate a seismic signal which would arrive at the time indicated by this lightly coloured blob. We should think, to Jeffries' words, should we believe that there is a layered structure on Mars? I think it's entirely reasonable given this data point, but all that Mars has given us is one data point, one impact, one set of wiggles, one lightly coloured blob, followed by some others. If this was the case, we could make an argument to build more complex models of Mars, and this is our best guess so far. So maybe Mars has a more complex interior. We're learning a lot of things about the 1D structure of the core of another planet. So what's the fate of InSight now we've used it to stare into the heart of Mars? Well, here is a picture taken and sent out by NASA and the University of Arizona, taken from orbit by the HiRISE imager. I'll just blow it up for you. That's InSight on the surface of Mars. It's not a selfie, it's taken from orbit. InSight recorded data for 4 years. It ran out of power because its solar panels slowly got covered by dust. The dust continues to accumulate. I think in a few years' time, we won't be able to see InSight at all. InSight therefore got switched off in 2022, or at least it went to sleep and stopped sending us signals. And that is the state of the data that we have available to us from Mars right now. But we've seen into the core of another planet in our solar system. So where are we going? What could Jeffries tell us? What should we think about? What do we disagree with? In a piece in Nature written on the occasion of the Silver Jubilee of King George V, I think, Jeffries said that comparing the position of geophysics in 1935 with what existed in 1910, while we're struck by the great developments that have taken place, we're equally struck by the fact that most of the theoretical advances are due not specifically to new methods, but to the fuller application of methods that are already known. I disagree slightly with this, moving on from 1935 to the present day. We have significant advances and developments of existing methods, but there are new things to come as well. So what's the future of core seismology? Where are we going? I think there are 4 different directions where core seismology will help us learn more about our planet. The first is new sensors. So I'm showing you here on the screen right now a mermaid sensor. This is a floating seismometer. It floats about 1.5 kilometers below the surface of the ocean and can therefore detect seismic signals where there is no land on which one could place a traditional seismometer. In the center of the screen, I show you seismic records of core transiting seismic phases detected by this mermaid, which then was floating out in the South Pacific. New sensors will help us understand more about the seismology, physical properties, and therefore the evolution of Earth's core. That's great. What else? More seismic phases. So I think it's going to be really important that we get more observations of normal mode frequencies and more observations of as yet unmeasured normal modes. You see in the map on the left-hand side of the screen, all of the earthquakes with magnitude 5.5 and above, which took place in 2024. This is last year's data set. We have more seismic sensors on the surface of the Earth than ever before. We will measure more phases. We will hopefully get more normal mode observations. And we should look for exotic seismic phases like P4KP. That's a seismic phase that does a whole lap around the outer core before escaping and being detected at Earth's surface. More seismic phase observations will help us better understand the core. Both the piece of work where we looked at the properties of Earth's outer core and the work where we looked at the properties of Mars's core were multidisciplinary efforts. And I think that's going to be really important moving forward. We combine thinking about seismology with thinking about mineral physics and thinking about how a planet evolves and what is cosmochemically reasonable for a planet. I think that multidisciplinary work must continue if we're to keep on better understanding the heart of our planet and the hearts of other planets. And indeed, I think that we will continue to explore the cores of other planets. I don't think it's going to happen immediately. I'd very much like some more data from Mars. That's not going to happen too soon. But I believe we will continue to seismically explore the cores of other worlds. And so I present to you an image from the PhD thesis in a publication by Kat Dupre of what could be going on in the core of Enceladus. Enceladus is a very small moon of Saturn. It's only got a radius of 250 odd kilometers. It likely has a silicate core, and the top of that silicate core may have actually been changed or serpentinized by interacting with the ocean water above it. So we should talk about what we believe a core really is. Does it have to be iron for us to call it a core? Should we think about silicate cores like this in the same way that we think about iron cores of the telluric planets? So if those are my ideas about the future of core seismology, what have I really said today? I posed some questions or some blunt statements at the beginning. I said that we've been thinking about the one-dimensional or radially dependent properties of the Earth for approximately 130 years, and we're certainly describing Earth's core better than ever before. But fundamental questions remain even about the one-dimensional radial properties of Earth's core. I said that we've been trying to think about Mars as a species for many, many millennia, but we only had 4 years worth of seismic data. With that seismic data, we've developed the first seismically informed models of Mars. But honestly, they are limited by the single seismic station and by the very small set of Mars quakes that we are able to detect. So I believe we've learned a great deal about the core of Mars and the core of Earth, but I believe there's more to do on both of those planets and further out into the wider solar system. And so I'd like to finish speaking there and ask that the questions are much nicer than they were from Eddington. Thank you for your time, everyone.
Thank you very much, Jessica. That was beautifully clear. Do we have questions for Jessica? Yes.
Thank you, first of all, for a very fascinating, very clear lecture. One of the first surface features of Mars is the apparent appearance of ocean features. And yet, where has all the water gone? Is there any seismic evidence that there may be subsurface water in Martian structure?
So there are certainly people who could speak better to these relatively surface-related stories than I, as a core seismologist, would. However, I'd say, first of all, that there are a number of models about what might be happening directly under the InSight lander, so relatively short-scale structure. Some of those models have a small amount of hydrated material present, others do not. The other thing I would say, though, is that really the history of Mars is very different to the history of our planet, primarily due to the absence of whole planet plate tectonics as we understand it. What we do see from the seismic results, and it doesn't directly answer your question, is that we have some small amount of hydrogen and some small amount of oxygen in the core. And so I want to be clear that those are likely primordial features. That is not where the oceans would have drained to. That water wouldn't have got the whole way through the mantle of the planet, although people have sometimes suggested it, but rather that we have a really complex body that we're seeing, where clearly the nature of water storage must be different to that on the Earth. Because on the Earth, we do believe that it could be possible for that hydrated material to travel very deep. Indeed, on Mars, we think that's likely different. Thanks.
John.
Put your hand up again, thanks.
Maybe this is a dumb question, but I didn't understand how in the case of the Mars events, how you were able to locate the origin, except for the case of the impact, of course.
So that's a very good question, a very good question indeed, because if you take an undergraduate class in seismology, they'll tell you that you need multiple seismic stations to detect the location of an event. And I've just told you that it was done with one. What you can do, and we would have liked more stations to be super clear, but what you can do is actually use the polarization of the energy to try and determine its back azimuth. So the direction in which the energy is coming from. So we know that P waves are compressional waves, and we understand the polarization of those. You can use, therefore, those P waves to tell you the direction the energy is coming in from, and then you can use the time separation of seismic phases to tell you the distance. So we do this by looking at the vertical motion, the north-south motion, and the east-west motion of each individual seismic phase. And then you can have a go at estimating back azimuth and get a full location, contrary to what any undergraduate lecturers may have taught you. And I've certainly said the same thing. This is not easy, and so only for quality A events were the amazing Mars Quake Service able to do this sort of work. There are many, many, many more events where a full location couldn't be developed because it wasn't possible to do those rather technical calculations. So the short answer is it's super hard, but with a whole bunch of seismic processing, you can get a decent idea.
Now, I can see other hands, but we're beginning to overstay our tenure of this this room. So, Jessica, you're going to be at the drinks reception afterwards?
Shall be, yes.
Please ask a question. I actually have a couple for you too, but I'm going to
Fine.
refrain from asking them. So just ask Jessica later. Thank you very much. That was a wonderfully clear talk. Right. Our last speaker today is Dr. Chris Lovell from the University of Portsmouth. He's a Dennis Sharma Fellow. His research focuses on numerical simulations of galaxy evolution, in particular how to model the electromagnetic emission from galaxies, whilst also leveraging the latest statistical and machine learning methods. He received a PhD in astronomy from Sussex in 2019, supervised by Peter Thomas and Stephen Wilkins, has held postdoctoral roles at the University of Hertfordshire and the University of Tokyo. He was awarded our 2004 Early Careers Award and for his work on forward modeling extreme star-forming galaxies. He's a member of the Euclid, Learning the Universe, Camels and Flares international collaborations. And his talk is called Accelerated Modeling of the Entire Observable Universe. So now you know why I'm worried about us running over time. Chris, over to you. I'll warn you with 5 minutes to go.
Sure, yeah. Thank you very, very much for having me. I'd just like to say that everything you just heard about the Earth's core is clearly wrong. It's obviously turtles all the way down. Sorry, Jessica. Couldn't resist. Yeah. No, what I'd really like to say is, yeah, a big thank you to the RAS, firstly for inviting me to speak to you today, but also for the Winton Award last year. It was a great honor. I'm going to talk to you a bit today about this sort of grand goal about how do we model the entire observable universe, and with thanks to many of the collaboration we just heard of. And I'd just like to say a quick word. My supervisor, Professor Peter Thomas, sadly passed away last year. I'd just like to shout out to him for his wit, his patience, and his integrity that made myself and many others into the scientists we are today. So let's crack on. So yeah, the main topic of this talk is modeling, but you know, this is what we actually see when we look at the universe. So this is SMACS 0723. It's a giant galaxy cluster at redshift around 1.5, seen by the James Webb Space Telescope. And this sort of image has essentially the whole of cosmic history contained within it. There are distant galaxies in here forming just a few 100 million years after the Big Bang. There's also stars in the foreground from the Milky Way. So there's a huge amount of information in an image like this. And this is 3 different bands from JWST combined together. And from data like this, combined with our simulations, we've built up this picture of the sort of history of our universe, from the Big Bang and primordial inflation through the dark ages to the formation of the first stars and galaxies a few 100 million years after the Big Bang, and then the sort of history of galaxy evolution that starts there and ends at the present day. Now, as I mentioned, hopefully this is going to work. Thank goodness it does. One of the things, or one of the tools that we've used to build up this picture have been what we call numerical simulations. So these are incredibly expensive computational tools that consume tens of millions of CPU hours on some of the largest supercomputers in the world, but essentially try to evolve our universe from some starting initial conditions and allow us to study representative populations of galaxies and compare them to the observations we've just seen to try and understand the processes that lead to these images of galaxies that we see. And I don't think I need to reiterate it to this audience so much, but the ingredients that go into these sorts of simulations are our understanding of the different constituents of matter and energy. So the baryonic matter that we're all made of and most galaxies are made of is only around 5%, and dark matter another 27% or so. Dark energy that drives the expansion of that universe. But essentially, we place all of those, in the most simple terms, in a box, and we combine it with some physical laws, be those gravity or the hydrodynamics of how gas interacts and heats. And let's play that again quickly. And essentially evolve it forward and see what happens, right? So, and given some, relatively tight constraints from the observations, we can actually generate realistic looking galaxies given these, these quite simple ingredients. This is a remarkable achievement of gravity evolution theory and cosmological modeling over the past 30 to 40 years. And it's worth highlighting, I think, the real challenge of doing this, okay? So the kind of scales that are involved in modeling galaxies truly goes from the very biggest things we see to the very smallest things, right? So on the biggest scales, we're talking about the large scale structure of the universe, this sort of cosmic web that galaxies form within, inside the nodes of this sort of web-like structure. As we go down this scale, we're going down to sort of galaxies that are already around 5 orders of magnitude smaller than this sort of cosmic structure, but clearly, still have a lot of detailed substructure within them. So if we go down again to the sort of scale of black hole accretion disks and stellar radii, we're talking now another almost 13 orders of magnitude smaller than this large scale structure. So if you want to simultaneously capture the impact of the environment on galaxy evolution, but also the physics that goes into how black holes accrete and have an impact on their overall galaxies, you have to be able to resolve all these scales. And going even further down, if you want to understand the chemistry going on in the interstellar medium within a galaxy or in the intergalactic medium, you need to understand the sort of chemistry going on and processes occurring on the scale of molecules, atoms, and ions. So in order to achieve all of this simultaneously is clearly impossible and will continue to be computationally impossible for probably the next few hundred years. But we can make some assumptions and we can start to target different areas of these scales to try and learn something about galaxy evolution. And so this sort of figure of merit is intended to sort of show the state of the art today. So the x-axis, we have the resolution of sort of what we call baryonic resolution elements, essentially particles of gas in our simulation. And then on the y-axis, we have the volume of the simulation. And you'll see there's this general sort of anti-correlation here. If you go to larger volumes, you have to sacrifice the resolution. And if you want to achieve high resolution, you have to sacrifice the volume. Now, what we would really like to do is probe right at the top here, which is being hidden by that. Can I throw that somewhere? Go away. That'll be a little bit better, maybe. We'd like to probe the very top of this plot. So you notice these lines here show the kinds of volumes probed by different surveys. So you notice Euclid deep and Euclid wide cover quite large volumes. Euclid wide very close to covering the entire observable sky. But we'd also like to ideally have high enough resolution to resolve sort of the process I just mentioned of pole accretion and stellar assembly. Now, clearly getting to the top right of this plot is kind of impossible. And what I'm going to focus on today are the simulations that sort of lie in this intermediate part here, right? So you have slightly sufficient resolution to model a lot of these processes, and also sufficient volume to start saying something interesting about the statistics of galaxies. So these kinds of simulations have had, sort of the flagship simulations of this type emerged about 10 years ago. And some of them named here on the left. And they've had a huge amount of success actually in producing a lot of these, what we call key distribution functions of the galaxy population. So on the left is the galaxy stellar mass function, which is essentially just the count of the number of galaxies of a given mass. And you'll notice as you go to the right here to higher mass, then these galaxies become rarer and rarer. On the bottom here, we have what's called the cosmic star formation rate density, which is essentially just the volume average star formation rate as we go back in time. So you notice that what we call cosmic noon here at sort of cosmic time of about 2 or 3 gigayears after the Big Bang, the star formation rate density is sort of peaks, it's at its highest, and it slowly starts to tail off towards the present day. There's a nice paper from around April Fool's Day last year where they also divide this into cosmic noon and cosmic breakfast and cosmic afternoon. So you can have a look at that one. And at the top here, I think there's the key one. These are sizes of galaxies. So stellar mass against the radius here on the y-axis. And so the key thing with these kinds of simulations is that not only can we say something about these global properties in a statistically sound kind of way, but we can also probe the internal structure of galaxies and their sizes. So it's a nice trade-off between these two things. However, there's a problem. So this is the Eagle simulation on the far left here. So this is one of those simulations I was just talking about, with a box showing its sort of volume here, compared to the kind of volume probed by the Cosmos Webb Survey. So this is one of the large programs on the James Webb Space Telescope at around sort of redshift 6 to 7. And you'll notice that they're sort of relatively comparable here. So the kind of environments probed by Eagle, you'll probably be able to capture in Cosmos Webb. This is now showing all of the different cycle 1 surveys from JWST. And again, it's looking a little bit bigger than Eagle now, but it's sort of still programming kind of the same volume. This is now Euclid wide, right? And you notice Eagle is all the way over there. So the main takeaway here is that, yes, Eagle is a much smaller volume than Euclid wide. But the thing to keep in mind is that Euclid wide is going to contain lots of different variations in here, rare regions that you simply cannot capture in a simulation like Eagle. Things like rare clusters or very rare early forming galaxies that you simply, you need a very, very large volume to be able to capture these rare events. So how do we still, achieve this very high resolution of the sort of Eagle-like simulation while still probing things that we're going to see with Euclid and be able to test it? So this is where FLARES comes in. FLARES stands for the First Light and Reionization Epoch Simulations. This is a simulation project co-led by myself and others at the University of Sussex, where we essentially take a slightly different approach. So rather than running a box, a periodic box with all of our ingredients in it, what we do is we take a very large dark matter only simulation. So this is a lot cheaper, doesn't have all of the galaxy formation and gastrophysics in it. And we select regions from that box of different rarities. And then we re-simulate them with all of the galaxy formation and gastrophysics included inside them. So that's what's shown here. These are 40 different regions selected from this very large box, from very sort of underdense regions at the top left here, you'll notice. So this is the density of the gas in this region, to these very, very overdense regions. And we include all of the galaxy formation physics that we care about with these. And the key thing about these is that we can now say something about the overall distribution from this large box, but using a much smaller amount of compute. So the plot on the left here is showing the distribution of what we call overdensities, essentially the density within spheres of this size across this whole dark matter only box, and essentially showing that our selection of regions with the black solid line. So we kind of over-select these rare regions, and we kind of over-select the underdense regions as well, while still getting a few of the mean density regions too. And then what we can do is we can measure statistics in each of these Zoom simulations and combine them together based on a weighting, essentially, which is slightly more complex than this, but essentially the ratio between that black line and the blue line. So we overweight our mean density regions and we underweight the rare regions. But what this allows us to do is to measure things like the UV luminosity function out to much larger dynamic ranges. So this plot is essentially showing it's the same as the galaxy stellar mass function, but now showing UV magnitude, essentially showing the brightness here. So from left to right is fainter to brighter, and then the relative number density of objects of that brightness, which you can't see, rarer. So as you go further down here, you're looking at rarer objects. Now, Eagle, the original periodic box, is shown by the gray dashed line here. So as we go to brighter objects, they tend to be slightly rarer. The boxes here are showing the relative, or sort of the kinds of areas of this plot probed by different instruments. So you'll notice that Webb here, the James Webb Space Telescope, is these yellow boxes at the top, kind of go to quite faint objects to the left of this plot, but don't probe very, very rare objects. So this is due to the fact that James Webb has a very narrow field of view, but is incredibly powerful and can probe very, very deep. Whereas something like Euclid is not able to probe quite as deep, but has a very wide field of view and is able to cover large regions of the sky. So it doesn't probe as far to the left, but it does probe these very, very rare bright objects. So, ta-da, that's where flares comes in. So now we're able to probe these sort of rare objects from Euclid that we simply weren't able to model at all with the previous approach. And we get statistically significant samples of these things we can now start to compare to Euclid when it comes out. So this isn't the only sort of thing that we can get out of this. Things like passive galaxies at very high redshift, so galaxies that have stopped forming stars, are very, very rare in the early universe. In the early universe, there's lots of cold, sort of primordial gas available for star formation. However, we have seen hints of these passive galaxies emerging. So flares is actually a very powerful way of exploring these kinds of galaxies that we simply wouldn't be able to probe with other approaches. So just to finish now, so you can see that flares is around this sort of resolution where we can start to study these things in detail. It's able to push up to this sort of target parameter space to the top right. And this parent box now is a comparable size to the Euclid-wide volume being covered. So that's all well and good, but most of what we've already seen here has been things like the galaxy stellar mass function. I did show the UV luminosity function, which is a bit of a spoiler. But essentially what I'm trying to say here is that the images here that we're seeing on the left are not what we get out of the simulation raw. Okay, in order to compare something like this on the left with something like this on the right, we need to do some conversion. And we can either convert our observations into physical properties, or we can convert our simulations into observations. So I'm going to try and make this point here with this figure of merit. So we have our physical models on the left that we use to build our simulations, and we have our observations on the right. Now, the kind of most traditional approach for studying or for making this connection is to take our observations, so this image of S-Max, for example, identify sources in this image, i.e. galaxies, and then perform inverse modeling, which is otherwise known as spectral energy distribution fitting on those objects to obtain physical properties, things like the stellar masses, star formation rates, or the chemical enrichment or age of those galaxies as well. And then you can do some modeling comparison then to your physical model. So this is the more traditional approach for doing this. This SED fitting step usually uses quite simplified models for the galaxies. It doesn't take into account any of these sort of numerical approaches that we've just been talking about. And so there's a lot of biases that can come into this particular step here. The other way is to go left to right. So we take the physics that our understanding of cosmology and galaxy formation, we run our numerical simulation to obtain some fields, whether that be the dark matter distribution or the gas distribution. And then we can either identify objects in those simulations that are galaxies, or we can model all the way to the observations at the field level, essentially. And essentially what that allows us to do then is to generate things that we actually see. So things like fluxes, the observed sizes of galaxies, their spectral energy distributions, or even imaging as well. So how do we actually carry out this step of taking our physical numerical simulations and generating synthetic observables? So you'll notice here, this is a spectral energy distribution of a typical galaxy. And the top left is sort of showing the Andromeda galaxy in a few different bands. You'll notice that depending on the wavelength that you're looking at this object, obviously it looks incredibly different and you're probing incredibly different physics. When you look at this in a 1D sense, the spectral energy distribution, you see it gets incredibly complicated, but there's essentially four main components to this. The first is stellar continuum emission. So stars of all ages contribute in a broadband sense to the overall SED. We also have nebular emission from H2 regions. These are star-forming regions covered with H2 gas. And it's also the impact of dust absorption and emission. So the absorption of dust essentially leads to attenuation in the optical and UV, and then re-emits that energy in the far infrared and sub-millimeter, to the far right here. And then AGM emission, which makes everything really complicated and horrible, and I'm not going to talk about. So in terms of the stars, there's essentially been a huge amount of work over the last over 50 years now in terms of what's called stellar population synthesis. So even before any numerical models of galaxy evolution emerged, Beatrice Tinsley was working on this approach of stellar population synthesis back in the late 1960s, and essentially is a way of estimating the aggregate emission from a population of stars. And there's a few ingredients that go into this. So you have something called your initial mass function of stars, which essentially tells you the distribution of masses of stars that are born in a given H2 region. You then have stellar isochrones, which describe how these stars evolve on the Hertzsprung-Russell diagram over time. And then finally, spectra of those stars at different types and throughout their ages as well. So once you've got your IMF, you know what the distribution of stars you have, you can know what they're going to evolve into, and you know what the actually spectra are going to look like. You can combine these all together to estimate this aggregate output from this single stellar population. What you can then do is combine this with the star formation history of a galaxy. So we know from a galaxy or from our models when the stars formed and of what ages. And so we combine these models together with this star formation history to produce the overall spectrum from a galaxy's stars. And so I just want to highlight Sophie Newman, who's a PhD student at Portsmouth, who submitted her first author paper this week, and essentially was using these SPS models from the Marston group, and is going to be using these to apply to numerical simulations. So the second component is this nebular emission. So this is essentially emission from ionized gas in these sort of H2 regions where new stars are forming. And what this comes out as is either a set of emission lines or nebular continua that contribute to the overall spectrum. And this is due to a plethora of physical processes within that gas that lead to either discrete lines or broad nebular continuum emission. And this is just an example from Sophie's work showing this now separated into the various components. So you can see this sort of broad nebular continuum with these sort of saw wave jumps in it, and then these individual lines that are associated with different chemicals within this H2 cloud. And then finally, dust attenuation and emission. So dust in a cosmic sense is essentially like cigarette smoke. So this top right image is showing a sort of dust or interstellar dust molecule. In the optical, what it does is essentially attenuates the light from the galaxy. So when you look at optical images You'll notice these dark bands in the image, which are due to dust attenuation of the background stellar light. But in the far infrared, we notice it as it's re-emitted as sort of thermal emission, which is shown here at the bottom for Andromeda as well, which basically traces the star formation emission. So we see attenuation in the optical UV and a re-emission of that energy in the far infrared. And so this is what that kind of looks like from the modeling sense. So there's a lot on this plot. Essentially, what we're able to do is mimic the observations from a wide range of different observatories. So on the far left, we have the color evolution of galaxies that would be observed by the James Webb Space Telescope, compared to some sort of early data here. We have IFUs. So these are what we call integral field units data cubes. So these are actually resolved images of galaxies, but also have a spectral component. So they are 3D images. And we can fully model this as well as the relative velocities of the gas in those galaxies and their stars. So that's shown at the bottom here is the SDSS project. We can create Hubble imaging. So this is a very nice image from Deshkin Narayanan's work, showing a sort of mock Hubble image of a spiral galaxy using dust radiative transfer to obtain this. And then we can go even into the far infrared and the sub-millimeter. So this is an ALMA mock image submitted by a master's student, actually, Parush. And on the far right, this is the 850 micron sub-millimeter emission from a galaxy. Great. Okay, I think we're going to skip some stuff. Apologies. So I'll quickly skip this. The only reason I put this on is because this is what I won the award for. So, so probably mention it really. So this is the 850 micron number counts. So these are the numbers are exactly the same as the other plots I've shown. The numbers of galaxies of different 850 micron brightness. This is incredibly hard to reproduce with hydrodynamic simulations for a very, very long time. But using a new simulation and a new radiative transfer approach, we were able to achieve something that isn't quite right, but is an awful lot better than a lot of the other previous approaches. And so this just kind of shows some of the value of some of these updated modeling approaches. And yeah, the redshift distribution is reasonably good as well. Okay, 5 minutes. So we've gone from numerical simulations, very simple ones on the left, including galaxy formation physics and also the forward modeling. There's an awful lot of parameters that go in at these various different stages, right? So we have things like the matter density of the universe and how matter clusters on the far left, all the way to the strength of dust attenuation, or the choice of which model for stars we use on the far right. So obviously there are choices that are made along this, but which ones are actually important, which ones actually have a big impact, and which ones on the far right, for example, could affect how we infer the things on the left. If we choose the wrong dust, do we get the cosmology wrong? And similarly, if we have the wrong cosmology, will we get the wrong inference of things like the dust attenuation? So one way of approaching this is, if you had a very, very large simulation, you can't really change lots of these parameters. It's too expensive. So another way of doing this would be to take smaller box simulations and change lots of these parameters at the same time. And basically apply machine learning methods to these to understand which parameters are most important. And this is an approach that's been taken by the CAMELS simulations. So CAMELS is a series of thousands of hydrodynamic plus dark matter only simulations where they modify both the cosmological parameters, but also the astrophysical parameters, and have used very modern machine learning approaches to understand and infer those parameters from the observables. So this is just showing a selection of these simulation boxes with these different parameters being varied. And you'll notice very briefly that they do show very, very big differences in the properties there. So CAMELS is composed of a series of different hydro simulations. This is just showing the impact of these different parameters that are changed on this cosmic star formation rate density. So the main ones they've changed are this omega matter parameter, the overall matter density, sigma 8, which controls the clustering, and then these parameters will control the strength of supernovae and AGN feedback. And one of the key things they do is they don't just take one model and modify these parameters. They use lots and lots of different models as well. So this video is just showing 8 different simulations of galaxy evolution. So I'd want to emphasize that the cosmology here is exactly the same. The only thing that's different is the galaxy evolution models that are applied on top of it. In blue is the density of the dark matter, and in red is the temperature of the gas. And so you'll immediately see already that these are very, very different. Right? So some of these models, you'll notice these sort of jets that are going off. Those are AGN feedback from supermassive black holes, whereas other models have a much more subtle effect. The thing to emphasize with this is that if you look at something like the galaxy stellar mass distribution, all these models produce something quite similar. So there's actually quite a lot of differences there. And I feel like I'm getting the rush. Okay, let's go for, so what we did is we forward modeled all of these sources from the simulation. So that's around 200 million galaxies, which I believe is the biggest set of synthetic photometry for a hydro simulation. We can create luminosity functions and colors, which is great. And we can show what happens when we change things like omega matter on the luminosity functions and colors. And then what we can do is we could plug this into a machine learning approach called simulation-based inference and ask, okay, given this set of luminosity functions, what parameters went in to produce it? And to rush very quickly over this, if you do that, you can actually you can invert this and ask, okay, what is the value, for example, of omega matter given these luminosity functions and colors? And the remarkable thing is that we get reasonably good constraints. So where this is close to the one-to-one line is where we actually getting very, very good constraints. And we can ask questions like, okay, where's most of the information? Is it in the luminosity functions or is it in the colors? And we find some very interesting trends here where we find that color information is actually really, really important, particularly for things like clustering. And I'll finish there, sorry.
Sorry to hurry you. Can you take a couple of quick talks, questions?
I'd love to have the time to take a couple of quick talks, but quick questions. Shoot.
Is that for Q?
Yep. Oh, okay. Yes. Thank you.
Fantastic. You're taking one of the bigger models as your initial conditions for flares. Is that how I understand it? You're taking one of the larger models as the initial conditions for flares, and that's where you're looking for those rare conditions. Are you finding it's other assumptions you're taking which leads to those rarer areas which you're looking for? Or is it the initial conditions, or is it some of the other assumptions which you're finding through SBI which leads to those things? It's a very complex situation.
Yeah, so the first order is the environment. So these regions, these flares regions are large enough that we're capturing, cosmologically representative still population of galaxies in those. So they are rare enough that they're producing rare galaxies, but you're right that for a given overdensity, there is still a lot of scatter in the predicted properties when you add in the galaxy astrophysics. So certain regions that you think will be very rare, there's actually a spread in the rarity of those objects. I haven't worded that particularly well. And then obviously as you add in the forward modeling, then that also increases that variance as well. So it's not a case of, it's very simple, a one-to-one mapping on just the overdensity. Yeah.
One more question.
Thank you. Thank you for the talk. Can you model the very early objects we see with James Webb, the massive black holes, etc.?
Yes, is the short answer. So flares, the name for flares, first light reionization epoch simulations, we basically stop the simulations at a redshift of 5. So it's very much focused on James Webb and early galaxies. And it has already been used to explore and place some limits on these very early galaxies. Flares actually remarkably seems to do quite well at matching some of these early results that suggested attention with our previous understanding of the sort of abundance and masses of early galaxies. So flares does slightly better than some other models. And we believe that part of that is due to our simulation approach. We're actually capturing these rare objects that James Webb is seeing and that other models aren't able to probe because they don't have the volume to do it. But With that said, there's been a few papers in the last couple of weeks where flares is still struggling to produce enough of these very massive things. So flares isn't, the end of the story, but it's certainly, I think, an important ingredient.
Okay, with that, I fear I have to wrap up. I'm just going to wrap up by saying that everything that you've heard today was beautifully presented and absolutely fascinating. So I think we should give a big round of applause to all our speakers. Oh, yes. Yes. I should say, if you're going over for drinks, pop in at the library, and Sean has prepared an exhibition about Chandrasekhar and, God, I've forgotten his name, Eddington. Oh, don't you love old age? Okay, so yes, Eddington, and there's some correspondence and things like that. Thank you for reminding me, Steve. Okay, thank you for all coming, and come and join us for a drink, and we'll see you the second Friday of next month.
No,
It was the first one. Do you know what?